In the last session, we have seen about Jacobian. So Jacobian is a matrix which relates the end effector velocity with the joint velocity. So end effector velocities, which is represented by x dot, with the joint velocities, that is q dot, right? So J is nothing but the Jacobian matrix. So we have seen how significant it is to determine the Jacobian of a manipulator, because the Jacobian matrix characterizes the motion of the manipulator. So in this session, we will learn about robot singularity. So having known what is the Jacobian, we can determine the singular configurations. That is the configurations of the robot where your rank of the Jacobian it decreases. So how will you determine the rank of Jacobian? Supposing J, that is the order of the Jacobian matrix, it is 3 cross 3, right? Then you know how to determine the rank of any matrix, right? So here, if the rank of the matrix is not of full order, say if the order of the Jacobian matrix is 3 and the rank of the Jacobian matrix is not equal to 3, that is if it is not of full order, then we say that this manipulator will have some singular configurations, or it will have some singular points, right? So or the configurations of the robot, there are certain values of q which will lead to the singularity condition of the manipulator. So what if this particular configuration is reached? So we know that it is singular condition. So what happens when the singular condition is reached? Let us explain this by an example. So let us consider that you are just using the robot to just paint up a line by using a paint gun, right? So in order to do this application, we want the manipulator to move along this particular path, at a constant velocity. If at all the velocity varies, if it is not uniform, then what happens, at some places you will be getting very thick line, and some places you will be getting very thin line, right? So the singularity occurs. So at when singularity occurs, the velocities of the joint velocity may go to infinite, right? So that is why it is very essential to determine the singular point. Say for example, let us take an example of an RP manipulator wherein we have already derived the Jacobian matrix. So let me write it again here. So x dot y dot, so which represents the end effector velocities, is equal to the Jacobian matrix. It is minus r sine theta cos theta, and here it is r cos theta sine theta, right? Times the joint velocities, that is you have, it is RP manipulator, so you have one revolute joint and one prismatic joint, right? So here, to determine the singular position, you need to know what is the determinant of the Jacobian, right? So what is the determinant of the Jacobian? So you will be getting minus r sine square theta minus r sine square theta minus r cos square theta. So that will be equal to minus r, right? So when will the rank of the Jacobian decrease? So when your that is determinant becomes 0. So when does the determinant become 0? So I'll just write it here. Rank of Jacobian decrease when determinant of J is equal to 0. So when this determinant of A will become 0 in this case, when your R is equal to 0. So suppose let us consider the manipulator. If the manipulator is first along the positive x-axis, this is the x-axis, positive x-axis, and this is y-axis. So when the manipulator is along the positive x-axis and you want to just make the manipulator to move to the negative x-axis, so at that time you want the joint configurations to vary so that your joint configuration will vary from 0 degree to 180 degree. So when the manipulator is trying to cross this origin, that is at that time your R may become 0. That is the radius is becoming 0. So at this point your joint velocities will become infinite. Right. So at this point the joint velocities will become infinite. So that is why it is not advisable to always have singular configuration. So we want the in this case in RP manipulator, so that it will never achieve this singular condition, that is R equal to 0. So R equal to 0 is a singular condition for RP manipulator. Next, the singularity, it can be either singularities, it is of two types. That is, it can be either boundary singularity or otherwise called as workspace boundary or workspace singularity, and the another type of singularity, it is internal singularity or joint space singularity. Right. So there are two types of singularities. So the first type, that is the boundary or workspace singularity. So when we are trying to reach to the farthest extent of the workspace, that is if this is the workspace limit, and then we are trying to, the manipulator is trying to reach to the farthest end of the extent of the workspace, then that gives a singular configuration. So that singularity condition we call it as boundary or workspace singularity. The next type of singularity is the internal or the joint space singularities. They are usually caused when the two successive axes of the robot, they get aligned. So what happens? So any rotation of one link, it will just lead to the counter rotation of the other, as because the axes are aligned, and then the actual joint location will be indeterminate. Right. So at joint space singularity, you will have infinite inverse kinematic solutions. So there will, at joint space singularity, you will have infinite inverse kinematic solutions, and also for small Cartesian motions you will attain infinite joint velocities. The joint velocities will be will be infinite. Right. So by analyzing the Jacobian of the manipulator, we can determine the singular positions of the robot, and we have also understood by this type how important it is to determine the singular position of the manipulator.